Biomechanics. Biomechanics is the application of mechanical principles in the study of living organisms.
Gait is the pattern of movement of the limbs in humans in a rhythmic motion. It is considered walking because the body maintains contact with the ground at all times. Inverted pendulum motion is due to the swing and stance phase, where whilst one leg is in motion, the other leg provides support.
The sagittal plane passes through the body from front to back, dividing the body into left and right proportions. For example, front and back movements occur in the sagittal planes, such as walking, as shown here by our participant. Running also includes the stance and swing phase, but adds a third phase, the aerial phase, where both feet are off the ground at the same time, as shown by our participant. The joints used in walking and running. The glenohumeral.
This is a ball and socket joint. It allows flexion, extension, adduction and abduction.
The humeral ulna.
This is a hinge joint. It allows flexion and extension.
The radial ulna.
This is a condyloid joint. It allows flexion, extension, adduction, abduction and circumduction.
The coxal.
It is also a ball and socket joint, so it has the same movement as a glenohumeral.
Tibiofemoral.
This is also a hinge joint, so allows flexion and extension.
Talaocral.
This is also a hinge joint.
Movement at the joints. Plantar flexion and dorsiflexion. Muscles used in walking and running. Quadriceps. Hip adductors. There are 3 parts to the hamstring, and they are semitendinosus, bicep femoris, semimembranosus, gluteus maximus, gastrocnemius, tibialis anterior. In this next clip, our participant is showing us the working muscles and joints being used while walking.
To work out the average speed, we need to take the distance travelled in metres and divide it by the time taken in seconds.
The joints labelled are glenohumeral, humero-ulnar,
Radial ulna coxal.
Tibiofemoral, talaocral.
For preparing our participant, joints needed to be marked out with tape. Variables that needed to be considered was that the tape applied can be easily identifiable.
The 3-4-5 triangle helps researchers to know where to position the camera at the correct position, which is at a 90-degree angle to the subject. The camera also needs to be at hip height. The participant holds a 1 metre rule which clearly identifies the endpoints, so the KA video program can scale the participant to real-world coordinates.
The shutter speed controls the time the image sensor is exposed to light. The higher the number, the faster the shutter speed is.
Angles are expressed in the following units: revolutions and degrees.
Here our participant is showing with a meter stick clear starts and endpoints.
In the arm joint, there is a smaller angle whilst running than there is walking at the toe-off phase. Due to an increase of flexion in the action of running, the angles are decreased.
Toe-off stage of gait begins as the toe leaves the ground. Represents the start of the swing phase. The talaocral and tibiofemoral joints, while walking, have bigger angles than running at heel strike phase. Because the flexion of these joints when running, the participant is in aerial phase, and does not have the supporting leg while the other leg is in swing phase, like walking.
The heel strike starts the moment when the heel first touches the ground at an angle shown in the picture. The difference of the angle of the tibial-femoral joint at the toe-off phase between walking and running is minimal because both pictures show the participant plant off Xanh to gain momentum to move forwards.
However, to gain more speed in the toe-off phase for running, the participant rotates their arms quicker to increase their velocity at a faster rate, whereas walking keeps a constant speed with the stance and swing phase in rhythm, keeping contact with the floor always.
Similar to the toe-off phase, when the participant is running at the heel strike phase, the humero-ulnar angle is still rotating round to gain momentum as a smaller angle, rather than walking when the angle is nearly a straight line.
Angular kinematics. This refers to the analysis of angular motion. It can be described in three variables: angular displacement, angular velocity, and angular acceleration. Angle displacement. This is the angle that a rotating body goes through. It is the difference between the final and initial position of the rotating body. It is measured in degrees. Angular velocity. This is the rate of change of angular displacement. It is equal to the angular displacement divided by the change in time. Here is the formula shown in this clip. Angular velocity is calculated in degrees but can be converted to radians by dividing it by 57.3. Angular acceleration. This is the rate of change of an angular velocity and is equal to the change in angular velocity divided by change in time. Here is the formula shown in this clip. Angular velocity is measured in radians per second squared.
This graph shows the angular displacement of joints from the heel strike to the toe-off and from the toe-off to the swing phase. Negative angles represent a clockwise rotation and positive angles represent a counterclockwise rotation. With exception to the radio-ulnar, all joints have opposite rotations. If the heel strike to toe-off was a clockwise rotation, then the toe-off to the swing phase was a counterclockwise rotation and vice versa.
This graph shows both the angular velocity and acceleration from the heel strike to toe-off phase and the toe-off to swing phase. As with angular displacement, if the heel strike to toe-off phase is a clockwise rotation, then the succeeding movement is counterclockwise and vice versa.
Table shows the angular displacement of joints during a run. This graph shows, in contrast to walking, both movements for the tibiofemoral and taloocral joints match. The tibiofemoral rotations are both clockwise and the taloocral ones are counterclockwise. The angles of displacement in the hip are also close. This suggests a more fluid, continuous movement in running, affected by the aerial phase as opposed to walking.
This table shows the angular velocity and angular acceleration from the heel strike to toe-off and from the toe-off to swing phase during the participant's run. As with the angular displacement during the run, all lower body joints continue the same direction of rotation through the phases. Also noticeable is that the size of the rotation is considerably larger during the heel strike to toe-off phase than is the toe-off to swing phase, where rotation is minimal. This is because of the aerial phase.
The air the participant breathes in travels through the nose where it is warm and cleanses the air entering the system. It filters nearly all particles out of the system to protect the lungs. It then travels through the pharynx, larynx, trachea, bronchial tree and into the alveoli.
Once in the alveolus, the air diffuses through a semi-permeable membrane into the blood capillary. This happens because the particles travel from an area of high concentration to an area of low concentration.
To help them diffuse quicker, the alveoli is one cell thick to get across the membrane quicker.
There is also a layer of fluid to help it process quicker across a large surface area. This is known as gaseous exchange. The oxygen particles, once in the capillaries, are picked up by the red blood cells. These cells are biconcave shapes which have a greater surface area and are 7.5 micrometers in size, so they can diffuse quicker. Inside the red blood cells, they have hemoglobin which carries the oxygen around the body and to the working muscles. With the erythrocytes having no nucleus, there is more room for the hemoglobin.
The oxygenated blood that comes from the lungs enters the heart through the pulmonary vein and on the left side of the heart, going into the left ventricle, which is then pumped out through the aorta from the electrical impulse towards the rest of the body. The blood enters the heart through the vena cava, entering the right atrium and flows through the right ventricle. When the erythrocytes deliver the oxygen particles to the working muscles, the hemoglobin's next job is to pick up the CO2 and remove it from the body via the veins, and up through the pulmonary artery where it is diffused into the alveolus and released into the air. In this clip, we are measuring our participant's heart rate while he is walking on a treadmill at a 1-degree incline. This graph shows an initial increase in the heart rate while walking, then a slight decrease at 200 meters. For the last 200 meters, another increase occurs in our participant's heart rate as he finished the walk.
The participant, while exercising, uses more muscles which are needing more oxygen in order to perform. This increases the heart rate of the participant, making them have a higher heart rate in running than walking.
This graph shows a steady increase in our participant's heart rate during a run at 11 km per hour on a treadmill for the length of 400 meters, with a 1-degree incline. The Vitale shows researchers how much volume of air the participant can expire in one breath. The peak flow meter shows a participant's maximum speed of expiration in one breath.
While the participant inspires, the ribcage elevates and the diaphragm flattens. However, while expiring, the diaphragm domes back up and the ribcage contracts.
A limitation to this is the 2D dimensional analysis. 2D analysis makes it harder to track the joints when transferring the video onto a KA 2D program. For example, during the participant's walk, the coxal joint may become hidden behind the participant's arm and was harder to track during the digitization phase.
To improve on this, use of 3D analysis would have allowed for a more detailed digitization process, which in turn would have allowed for a more accurate analysis of the participant.
Another limitation is the planes of movement. During our analysis, we only studied the participant using the sagittal plane. This limited the amount of data we could collect on their movement. Another limitation is clothing. The clothing worn by the participant during the film phase made it harder to pinpoint the exact position of the joints with the markers, as when the clothing moved, the marker would move as well, causing a distorted image. An improvement to this would be to wear clothing that didn't move during testing, allowing for more accurate analysis.
Frame rate. This was a limitation, as a higher frame rate allows for a more focused image of high-speed movements, but reduces the light in the video. Whereas a lower frame rate lets more light into the shot, but reduces the focus in high-speed movements.
An improvement to frame rate is shutter speed. A more specific choice of shutter speed would have allowed for a greater focus on the joints in the analysis stage.
A limitation was blood pressure. As a group, measuring the blood pressure of our participant would have allowed us to calculate stroke volume and cardiac output which would have allowed us to more accurately assess the physiological differences between walking and running.